To enable high-performance and scalable blockchains, we need to step away from traditional consensus-based fully replicated designs. One direction is to explore the usage of sharding, in which we partition the managed dataset over many shards that, independently, operate as blockchains. Sharding requires an efficient fault-tolerant primitive for the ordering and execution of multi-shard transactions. State sharding is a technique that can be used to parallelize consensus agreement to increase throughput. However, this parallelization is only possible if the method of sharding used enables separation of commands that are unrelated and thus may be safely processed in parallel. Scalability through parallelism. Parallelism requires an application layer that specifies the dependencies between commands. Radix Engine is one such application layer. The Radix Engine supports logic that defines predictable, correct results on ledger in response to requests. The logic is based on a finite state machine, or simply a state machine, is a mathematical model of computation. It is an abstract machine that can be in exactly one of a finite number of states at any given time. The finite state machine can change from one state to another in response to some inputs. The change from one state to another is called a transition. An finite state machine is defined by a list of its states, its initial state, and the inputs that trigger each transition. A Radix node combines a Radix engine as application layer and Cerberus multi-shard transaction processor for the highly partitioned Radix ledger. Cerberus provides serializable transaction execution, thus opening up the possibility of safe parallelism of consensus through state sharding that substantially reduces throughput limitations. A Radix node includes the following basic components. First, decentralized application. Second, Radix engine as application layer. Third, Cerberus as multi-shard transaction processor. Fourth, hot stuff or other Byzantine fault-tolerant consensus provider. In a shard design, resilient blockchains hold only a part of the data. Local decisions within a cluster are made via traditional practical Byzantine fault-tolerant consensus, whereas multi-shard transactions are processed via Cerberus. We name local Cerberus a single Byzantine fault-tolerant instance patterned after the Byzantine fault-tolerant design of hot stuff. The local Cerberus instance on a single shard that, operated in isolation, provides the same optimistic responsiveness and linear messaging complexity of hot stuff, as applied to a single blockchain. We have also independent local Cerberus instances operating in parallel. And finally, there are synchronized multiple local Cerberus instances. We have also mergent Cerberus when we add, first, synchronization primitives between multiple local Cerberus instances. Second, model the synchronized combination as a single Cerberus instance. The emergent Cerberus behaves like a single cross-shard Byzantine fault-tolerant instance. Parallelize emergent Cerberus instances across shards, enables massive and safe parallelization of the consensus process across the network. Particles and atoms. Transactions of the Radix engine create data structures called atoms in the Radix universe. Every atom consists of discrete objects or particles. Particles are finite state machines, input or output. Each particle being initialized has a neutral state. When a particle is being used as input, its state is up and is also marked as green. In cases when is being used as output, its state is down and marked as red. The Radix engine as an application layer dictates which input or output pairs are valid. Cerberus enforces the atomic commit of updating the state of multiple particles, either up green or down red. Atoms must be committed or rejected by Cerberus consensus atomically. Either all particles within the atom are valid and the atom is committed, or one or more particles are not valid and the atom is rejected. Nodes and shards. Cerberus assigns one real physical shard to every node. One-to-one mapping of particles to shards is used. In practice, mapping nodes to computing devices, with only one shard per device, would be an inefficient use of resources. The shards represent virtual particles that are typically inactive. Most computer hardware is capable of serving a very large number of shards simultaneously. Nodes having more computing resources can have even a full replica of the ledger, the radix universe. Shard virtualization. To retain the simplicity and correctness, Cerberus virtualizes an arbitrary set of single shard nodes in every physical node. The virtual nodes behave exactly as their physical counterparts would, with the only difference being that multiple virtual nodes map to the same physical device, with the same address and public key. To provide multi-shard transaction processing with high throughput in practical environments with a large number of shards, including permissionless networks, Radix uses variants of the original Cerberus concept. They are Core Cerberus, Optimistic Cerberus and Pessimistic Cerberus. Using these variants, the network will be able to adapt to the needs of specific use cases. Core Cerberus, simple yet efficient transaction processing. Core Cerberus uses strict environmental requirements to enable simple yet powerful transaction processing. Operates perfectly with respect to all transactions proposed and approved by well-behaved clients, but does not provide any guarantees for other transactions. To minimize the coordination necessary for multi-shard ordering and execution of transactions, Core Cerberus combines the semantics of transactions in the object dataset model with the minimal coordination required to assure shard applicability and cross-shard consistency. This combination results in the following high-level three-step approach towards processing any transaction. First, local inputs. Every affected shard locally determines whether it has all inputs from shards that are necessary to process the transaction. Second, cross-shard exchange. Every affected shard exchanges these inputs to all other shards, thereby pledging to use their local inputs in the execution of transaction. Third, decide outcome. Finally, every affected shard decides to commit transaction if all affected shards were able to provide all local inputs necessary for execution of transaction. The second step, cross-shard exchange, involves waiting for other shards. Hence, there is the danger of deadlocks if the other shards never perform the cross-shard exchange step. To assure that, we employ two techniques. First, internal propagation. To deal with situations in which some shards did not receive inputs to process the transaction, for example due to network failure or due to a faulty client that fails to send inputs to some shards, we allow each shard to learn transaction inputs from any other shard. Second, concurrent resolution. To deal with concurrent transactions, we allow each shard to accept and execute transactions for different rounds concurrently. Although the design of Core Cerberus is simple yet effective, we see two shortcomings that limits its use cases. First, Core Cerberus operates under the assumption that any issues arising from concurrent transactions is due to malicious behavior of clients. As such, Core Cerberus chooses to lock out objects affected by such malicious behavior for any future usage. Second, Core Cerberus requires consecutive consensus and cluster sending steps, which increases its transaction processing latencies. Next, we investigate how to deal with these weaknesses of Core Cerberus without giving up on the minimalistic nature of Core Cerberus. Optimistic Cerberus, robust transactions processing optimized for cases in which there are no concurrent transactions. In the design of optimistic Cerberus, we assume that malicious behavior is rare and we optimize the normal case operations. Optimistic Cerberus provides a recovery path to deal with concurrent transactions without locking out objects. Optimistic Cerberus takes into account reported malicious behavior and makes cross-shard coordination within a single consensus round. The consensus round runs at each affected shard, minimizing transaction processing latencies. Pessimistic Cerberus, transaction processing in environment where malicious behavior is common. Pessimistic Cerberus adds sufficient coordination to the normal case operations to enable a simpler and localized recovery path. It is capable to recover from attacks at lower cost, at the expense of increased complexity in normal case operation. Core Cerberus requires consecutive consensus and cluster sending steps. Respects all transactions proposed and approved by well-behaved clients. Locks out objects affected by concurrent transactions. Optimistic Cerberus does not require any additional coordination phases in the well-behaved optimistic cases. Optimized for cases in which there are no concurrent transactions. Does not lock out objects affected by concurrent transactions. Provides a recovery path to deal with concurrent transactions. Pessimistic Cerberus adds sufficient coordination, serialization of commands, to the well-behaved cases. Operates in a general-purpose fault-tolerant environments. Provides a recovery path to deal with concurrent transactions. The design of these variants of Cerberus is geared towards processing unspent transaction output-like transactions in shard distributed ledger networks with minimal cost, while maximizing performance. By using the properties of unspent transaction output-like transactions, both Core Cerberus and Optimistic Cerberus are optimized for cases with fewer expected malicious behaviors, in which case they are able to provide serializable transaction processing with only a single consensus step per affected shard, whereas Pessimistic Cerberus is optimized to efficiently deal with a broad range of malicious behavior at the cost of a second consensus step during normal operations. Both variants Optimistic Cerberus and Pessimistic Cerberus may be productive directions for consideration for different network deployment situations depending on desired trade-offs. The core ideas of Cerberus are not tied to any particular underlying consensus protocol. The internal consensus mechanism that the shards use is irrelevant. They even can be mixed. Each of the protocol variants have excellent scalability in practice, even when exclusively dealing with multi-shard workloads.